Welcome to Future Legacy.
Despite the ubiquity of computers, paper still occupies a central role in our everyday lives. It's used in a dizzying array of products, from newspapers and calendars, board games and food packaging, to notepads and post-it notes. Of course, unlike dynamic computing technologies, paper is static. It's a passive medium that has no inherent interactivity or computational power. We present a new approach to bring the digital and paper worlds closer together, specifically by enabling paper to track finger inputs, and also draw an input with writing implements. Importantly, for paper to still be paper, our method had to be low cost. We achieve this by coating paper on one side with a thin, uniform, and low-cost conductive layer. We identified two materials compatible with our approach. The first is conductive plastic film, which can be laminated onto paper as a backing. The second material is a carbon-loaded paint, which can be transferred onto paper using a variety of techniques, including silk screening, offset printing, and spray coating. These coatings could be applied at the mill en masse before paper is cut from bulk rolls into, for example, notepad paper stock. For either method, we need to augment the paper with traces that connect to points around the periphery of the sensed area. Our early prototypes were made by hand using wires or copper tape, but we quickly moved to methods that are more compatible with industrial processes like printing and die cutting. These approaches cost as little as 30 cents per sheet for the small volumes we created, but could cost dramatically less in volume. We believe this borders on the feasibility of a single-use touch panel, one that you can write all over and then throw away. Ultimately, the conductive layer and the traces coming from it connect to a sensing board which can be reusable or embedded inside an object such as a book. Our sensing approach is based on electrical field tomography. This works by emitting a small electric current into the paper's conductive layer using a pair of electrodes. The sensor board then measures the voltage at all adjacent electrode pairs. This process repeats for all possible current-emitting pairs, resulting in a mesh of measurements. When a conductive object touches the paper's surface, like a finger, some electrical current is shunted due to capacitive coupling, causing a localized reduction in voltage, which manifests in the sensing mesh. Using tomographic reconstruction, we can create a 2D sensor image revealing touch locations. We can even estimate applied force and multiple contacts with sufficient separation. We built a variety of example applications to highlight the possibilities and implications of our approach. For example, we can augment standard printer paper with the ability to track writing implements. Here, we've created an interactive exercise which features both multiple choice as well as fill-in-the-blank questions. This could allow grades to be automatically computed and even allow for real-time instructional feedback. Our technique can also scale to smaller sizes of paper. For example, we can digitize ink on this post-it note. Large sizes are possible too, like this newspaper. In this example, users can press printed buttons like posting to social media and adding to one's reading list. Beyond writing implements, we can also sense tokens, like in this board game example. We can track the state of the game, helping children to learn the rules, and also add to the experience through, for example, sound effects. Please see our paper for more details.